Parametrics. Parametrics are used for different things, but one thing that we can use parametrics for in pre-calc is to graph ellipses, hyperbolas, and sideways parabolas. We can't do that when we're just dealing with functions, right? You can't graph those on your graphing calculator. But when we get into parametrics, we can graph those kinds of equations. Also, parametrics are used to simulate real-life activity. For example, you're going to do a lot of problems that are baseball problems that they talk about. If the ball has been hit at a certain angle, and will it go over the wall, or will it hit the wall, or will it drop inside the baseball field? You can actually show that on your calculator, because you can show the wall on your calculator, and you can show the ball either going over or hitting or whatever it does. You can also simulate runners, like who's running faster, and you can show the two separate runners on your calculator. So when we get into this, you're going to have several different, I don't want to say projects with it, it's more like problems. Like we have the spider and the fly problem. Does the spider catch the fly? We have the baseball problems. We have a basketball problem. We're also going to graph a pumpkin, and then talking about the project. Whether you do the project or not, I think that if we don't do it, I'm going to go ahead and pull projects out from last year so that you can see what I'm talking about when we talk about this project. The project is with all parametric equations. You cannot use regular equations. You use parametrics. And what happens is with parametrics, you can do all kinds of cool things with your calculator. There was one project years ago that they did a lion, and they had the head, the body, and the tail, and they made the tail wag back and forth. There was another one with a bomb that blew up. And when I say blow up, what I mean is when they pressed a button, it made all kinds of graffiti things on their calculator. It looked like it was blowing up. So with parametrics, you can do some really cool things. And even if we don't do our project, we'll get into some of that. If you do your project, if we do have time, then you'll get into it even deeper. So to begin with, parametric equations, we're not dealing with x's anymore for our variables. We are now dealing with t's. We use t's for the variables, and we call t the parameter. These right here, the x of t equals t squared and the y of t equals t squared minus 3t, those are parametric equations. Every time you do parametrics, you have two equations for one. Okay? You don't just have one equation, we have two to make our graph work. To graph without a graphing calculator, you would plug the t values in, and whatever you get for x would be your x value, whatever you get for y would be your y value. So if I plug negative 2 into the x equation, I would get 4. If I plug negative 2 into the y equation, I get 10. So the point that I would graph would be 410. Okay, so you all know how to plug points in. I'm just going to give you the points. If you plug in negative 1, you get 1, 4. If you plug in 0, you get 0, 0. If you plug in 1, you get 1, negative 2. And if you plug in 2, you get 4, negative 2. Okay, so without your calculator, we would graph these coordinates for our parametric equations. So go ahead and graph your points. Okay, when you graph, your first point is 410. Your second point is 1, 4. Okay, and so stop right there, because when we graph parametrics, we also want to know which way they're graphing. Because I started with this point here, this is graphing this way. And you're going to see little arrows in your book on the graphs, and because that's showing you which way it's graphing. Okay, my next one is 0, 0. 1, -2, and 4, -2. So it's going to say connect the points with line segments. So we connect the line segments, and then we would have these little arrows showing which way it's graphing. Okay, so what I want you to do is get your calculator. Okay, when we graph, or every time you have looked at your calculator, you've been in function mode. Okay, this is what yours looks like. So you want to be in parametric mode. So you're going to cursor over to the AR, and that's parametric mode. Okay, next, go to your window. I want you to look at that because that's different than what we usually deal with. Now we have a T-min and a T-max and a T-step. So your T-value, your smallest T-value is -2. So we're going to use -2. So really what happens here is instead of X being my domain now, T is now my domain. And I'm going to 2. Okay, the T-step, I want you to kind of experiment with that because I want you to see what happens. So go ahead and go to y equals. And you see how you have X sub 1 and Y sub 1? Okay, well we have 2 equations and we're going to put those in. The T is the same thing as the X on your calculator. So you're going to do T squared. And then you're going to do T squared minus 3T. Okay, and go ahead and graph. And does that look like our graph? What we wrote here? Okay, so next. Go back. My Y value is kind of messed up. I'm going to change that to 10. And then I want you to go back to that T-step and change that T-step to 0.01 and graph. Do you notice anything different? What? It's slower. Okay, now do this. Go back to your window and do 0.001 for your T-step and graph it. It's really slow. So what do you think is happening? The smaller I make my T-step, what happens? It's more accurate. It's picking up more and more pixels. It's going slower and slower and picking up more and more pixels, so it's more accurate. Okay, so that's going to take a little while, so do this. Go second off, and it's going to stop it. And go back to your window, and let's change the T-step to 1. Okay, graph that and see what happens. That was fast, right? So the bigger your number, the faster. But put in 2. What happens there?
Oh, it's like...
It's not picking up all the pixels. So the bigger the number gets for your T-step, the fewer the pixels it picks up. Okay? Okay, now I'm going to do 5. And look at this. Okay, when you do 4, it's a straight line, right? And then when you do 5, it's a point. And the bigger you get, then there won't be anything on there. Okay? So that's what your T-step does. And I can't tell you that you always use 0.1 or 0.01. It just depends on what you're graphing, as you're going to see as we progress into this. But the T-step picks up the pixels and makes it more accurate or less accurate. Okay, so go to the next page. This is an ant that's walking across the graph paper, so there's position at a given time t in seconds. It's given by x of t equals t minus 2, and y, it should be y of t equals t squared minus 2 for 0 is less than or equal to t is less than or equal to 5. So I think we all know how to plug in. So I'm going to give you those values. If you plug in 0, you're going to get -2, -2. You plug in 1, you get -1, -1. You plug in 2, you get 0, 2. You plug in 3, you get 1, 7. You you plug in 4, 2, 14. And if you plug in 5, 3, 23. Okay, we're going to go ahead and graph it without the calculator, and then we'll graph the calculator. Okay, so I'm going to go through and I'm going to plot the points. The first one is -2, -2, so that's where my graph is starting. The second point is -1, -1. So what this tells me is that that ant is walking this way. Okay, 0, 2. 1, 7. 2, 14. And 3, 23. Okay, so that's what we did for the first one, B. C says calculate the length of each segment. So what would you have to do to calculate the length of each segment? Distance formula. We're not going to do that. Okay? You know how to do the distance formula. Because once you do that and you find the length of each one of those segments, you're going to add it together to find how far the ant walked. And when you do that, you should get 25.80 units. Okay, so your next question says, how can you make the estimation of how far he walked more accurate? What do you think? What if you did smaller intervals of time? Instead of like 0 to 1 second, you maybe went from 0 to half of a second, okay? So it would make it more accurate when you did the distance formula and you added them together.
It's like two step, does that mean it's small, it's like two step,
And then using distance equals rate times time, approximate how fast the ant was walking. We're going to go ahead and do that because distance is 25.8. You don't know the rate, that's what we want to find. Time is 5 seconds. So we're going to divide both sides by 5, and when you do, you get 5.160. And it's units per second. Okay, so what I want you to do is go back and put those two equations in your calculator. So you should be in parametric mode, and we're going to put them in. Okay, your t-value, your smallest t-value is 0, so on your window, t-min should be 0, and your t-max is 5. T-step, I'm going to go back to 0.1. And I want you to go ahead and graph it and see if you think your complete graph is on there. You think all graph is there? What do you think? Devin? No? How come? Okay, because what about our y-max is a 10. What is the y-max on your graph? 23, right? So we need to go to window, and we need to go to y-max. I'm going to change it to 30. And now I'm going to graph it. Is that my complete graph for my ant walking? Okay, Gavin said that this was a parabola. If you extended it, would it be a parabola? So this is what I want you to do. You see these two equations? You have x equals t minus 2, and you have y equals t squared minus 2. We can eliminate the parameter, and when we eliminate the parameter or we get rid of t, we will have a rectangular equation, what we're used to. So in order to do that, we are going to solve for t in one of these two equations. Well, it's easiest to solve for t in that equation, so we have t equals x plus 2. After we solve for t, we're going to take that and we're going to plug it into the other equation. That's y equals x plus 2 quantity squared minus 2. Is it a parabola?
Yeah.
Yeah, that's Vertex form for a parabola. So if you went to your calculator, changed it to function mode, and you put this in, it should look like that, except for the fact that it's going to be a whole parabola. You would have to restrict it to get that. So x would have to be greater than or equal to negative 2 for yours to look like that on function mode. Okay? So, okay, if you're going to do it in function mode, then you would do comma, and then these have to be in parentheses. No, it's not comma, it's division sign, right?
Yeah, and you do like,
Okay, and then it should restrict it. Okay, next, go to, we already did this, it's a parabola. And we already found the equation. Okay, domain and range. Domain would be from, in function of negative 2 to what? 3. Okay, and your range would be from negative 2 to 23. Okay, problem number 2 on your graphing calculator, put these two equations in, and this is your T min and T max. So go to y equals
okay. We have to do it on 2.
do you have to do what?
Let's do it on 2. On 2.
No, because you don't have two calculators. I don't know why she put that in. Okay, so next, on your windows, you're going to go from negative 3 to 3. And I'm going to leave my t-step at 0.1. And I'm going to graph. And what kind of curve do you think this is? Linear. Okay, so watch what happens. X equals t. So if I plug x in, it's y equals 3x plus 1. Is that linear? Yeah. Okay. What they want you to do is put it in to function mode, y equals 3x plus 1, and put this one in and see what happens. Well, what's going to happen? They're going to be the same exact line, right? If you go to window and you change your y max back to 10, okay, that's what it's going to, it has a y-intercept of 1. That's what it's going to look like if you did y equals 3x plus 1, right? So they're the same graphs. Okay, next. Put those into your calculator. T minus 2. And 3t plus 1. Okay, what kind of curve is it? Linear? Okay, so if I solve for t, I would have t equals x plus 2. If I put that into y, I would have 3x plus 7. So it's linear. Okay, next, it says reflect the curve across the x-axis. Well, think about this. If you had a point, and you were going to reflect it across the y-axis, what changes, x or y? Y. And if this is 3 up here, this has to be -3. So, if I'm looking at these two equations, which one would I have to change? The x equation or the y equation? The y equation. And I'm going to make them both negative, right? Okay, so if you want to check it, you can to see. Because okay, so on part B, it says reflect the curve across the y-axis. So which one's going to have to change, the x equation or the y equation? The x. So we would have x of t equals -t plus 2, and y of t equals 3t plus 1. Okay, and then part C. Translate the curve 2 units up. Are you working off the y or the x? If you're moving it up, y or x? Y. Hold on, I'm just on. Okay, so plus what? Plus 3. Wow, Caleb. 3 units left. Which one am I going to work off of? Yes. And it's going to be 3, 2, or, I'm sorry, 2 what? 2 minus 5. Because you're going this way, so you're subtracting 5 from the 2, okay? From the -2. Okay, so parametrics. A lot of the parametrics that we're going to do will be done in class because you don't have a lot of book work to go with them. Today's assignment is going to be a worksheet 6162 over vectors, and it'll be due on Thursday. But guys, I need you to make sure you have your calculators with you, and then when we have book work, make sure you have your book with you. So check your assignment sheets.